Okay, good morning class. So let's start the tutorial class today while we are waiting for the other students. So welcome back to school. I hope that you did have a good time during the spring break. Because it's been almost a week since your last class, so I would like to give you a review or overview on what you have just learned right before the break. So this, you may treat this as just a summary of those formulas that you've learned so far about how we can calculate the confidence interval under different scenarios. So most of the time, when you are given a question asking you to calculate a confidence interval, what you need to do is to identify the correct formula that you can use. Then the rest, once you can identify the correct formula or the approach that you can use, the rest will be just merely substituting numbers and do the routine calculations. So we have the so-called one sample problem. When we have a single sample, you have the data from the single sample. And when you are told that the sample was drawn from a normal distribution, then we can use either this formula or this formula to calculate the confidence interval for the population mean, depending on whether the population variance is given or not. If the population variance is known, we use this formula, then you can directly use the population standard deviation sigma. If it is unknown, we replace it by the sample standard deviation. But after we replace it by the sample standard deviation, the quantile here, originally this is the normal quantile, which is obtained from the normal distribution. So this is the standard normal. So when we partition it into three parts with the area on the left-hand side of this point equal to half alpha, on the right-hand side of this point equal to alpha over 2, and then the area, the coverage in between become 1 minus alpha. This number is the quantile, Z 1 minus alpha over 2. And this is minus Z 1 minus alpha over 2. This is the notation of the meaning of this quantile. It can be computed using R, or you can directly look it up from the standard normal distribution table. Now, if in case the variance is unknown, we replace the standard deviation, population standard deviation by the sample standard deviation. The quantile we use will not be from the normal distribution anymore. Instead, we need to find it from the student T distribution. So we have a quantile from the student T distribution. You can also look it up from the student T distribution table or by using R. But for the T distribution, besides the coverage of the value of alpha, it also depends on the sample size. We have a so-called decrease of beta here, which is equal to the sample size minus 1. And for the details of the derivation of this formula, you can refer to the notes. Now, besides finding the confidence interval for the mean, we may be interested in finding the confidence interval for the unknown population variance, which is given by this formula. Now, notice that this formula may not be exactly in the same form as the one that you find in the lecture notes. The reason is that in the lecture notes, the numerator here is represented by this sum of deviation. Sum of the square deviation from the mean. Now they're exactly the same, because if you divide this quantity by n minus 1, it will be the sample variance. So they are just different representation of the same formula. So in the lower boundary and the upper boundary of this confidence interval, we have the same numerator, but the denominator are obtained from the chi-square distribution table or by using the R. So we also have the degree of freedom here, given by the sample size minus 1. So this is a scenario when you will have a single sample drawn from a normal distribution. Now, sometime in the question, you are not told that it is drawn from a normal distribution. It is not mentioned about the normal distribution for the population. But we can still use the normal approximation in case when the sample size is large enough. When we have a large sample drawn from an unknown distribution with unknown population mean and the population variance sigma square, then we can approximately calculate a confidence interval for the population mean. If the population variance is known, then we can use the same formula as before by using the normal approximation. And if the population variance is unknown, then we replace the sigma by the sample standard deviation S. But this time, we don't need to change the quantile into the T quantile. The reason is that when sample size is large, the degree of freedom is also large, so that the T distribution will converge to standard normal. Now, for a single sample problem, besides the confidence interval for the mean, we may also want to estimate the population proportion. So in case when you have a sample from the Bernoulli trial, you have a sequence of Bernoulli trial as your sample. Each observation is just a classification into yes and no, success and failure. And if we want to estimate the probability of yes, probability of success, proportion of success, then the confidence interval will be computed approximately using this formula. And notice that this H bar represents the average of those 1 and 0 observations, because for a Bernoulli trial we have 1 or 0. And the average of this 1 or 0 is just the sample proportion. So the formula is the sample proportion plus minus the normal quantile multiplied to this expression. So you can see for the population mean or population variance, or population proportion, the confidence interval takes a very nice and regular format. We usually will have a quantity as a point estimate of the unknown parameter we want to estimate. And plus minus a quantity with two components. One of them is a number obtained from the table, a quantile. Another part here is actually the standard error of this estimate. So usually for the mean or the proportion, the confidence interval will take this regular format. So this is just a summary of what you've just learned right before the break. Now, besides the single sample problem, sometimes we may want to compare two samples. So we have two independent samples drawn from the normal distribution. So suppose you are told that we have two samples, each of them was drawn from a normal distribution. These two normal distributions, they may have their own mean and own variance, denoted by these notations. And if we want to construct a confidence interval for the difference in the mean, so that we can compare the population means, then we have this different scenario for different formula for different scenarios. In case when the population variance are both given, then the confidence interval will be the point estimate of this difference using their sample counterpart, plus minus a normal quantile, multiplied to a quantity which is essentially the standard error of this estimate. Here, M and N are the sample sizes of the two samples. So this will be simple, but most of the time, the population variance are unknown. And we also have two different scenarios, even when the population variance are unknown. When they are unknown, but you believe that they are the same. You have two populations, they have unknown population variance, but we assume that these variants are actually the same. Then, the confidence interval for the difference will be computed by using also the sample counterpart, difference in the sample mean. Plus minus, this time we have a T quantile. But the degree of freedom here is actually combining the degree of freedom of the two samples. So we have the sample size add together minus 2. And then we have a standard error computed as SP multiplied to this quantity, where this SP is actually the pooled sample standard deviation. Pooling the two sample variance together to compute a single sample variance. And then we take the square root. So you may find the details from the lecture notes for the derivation of this formula. And I also find that in the lecture notes, it also mentioned about how we can deal with the scenario when the population variance are unknown, but also unequal. When the population variance are unknown and unequal, for the two sample comparison, we have this formula for constructing the confidence interval for the difference in the population mean. Now this time we also have a T quantile here, but the degree of freedom is computed by using a very complicated formula here. I don't know whether you will be asked to do this kind of tedious calculation or not, but for completeness, because I find that it also appears in the lecture notes. Actually, this is called Acetyl approximation. And this expression here, besides the quantile, this quantity is just simply the standard error of this, when the sample variance are not assumed to be the same. And finally, for two sample comparison, we may also compare two population proportions. From two populations, we have two samples independently joined from two populations, and we are interested in comparing the proportions. And the confidence interval is obtained by this. Here, X bar is the sample proportion of the X sample. Y bar is the sample proportion of the Y sample. We compare these sample proportions to estimate this difference in the population proportions. Plus minus a quantity which is obtained as the product of a normal quantile. And this quantity is just simply the standard error of this estimate. So you learn a lot of formula. So the crucial operation is to identify the correct way, the correct formula to do the calculation. Is there any question? So these are the formula that you should have learned so far about confidence interval. And of course, there are much more different scenarios. You will learn more and more formula later. So I guess you have some idea on what is going on. So maybe we start with a later question, with question number 6 on the worksheet. So for the worksheet number 9 here, you may try to work on question number 6. Just identify what scenario this is, and to use the correct, to pick the correct formula to tackle this problem. Okay, I've seen that some of you are on the right track because you can pick the correct formula. The rest will be just routine calculation. So maybe I will walk you through this in details. Now, first of all, in this question, we identify some keywords. It says that the blood pressure is normally distributed. So that means you are told that the population, the sample is drawn from normal distribution. And you are also told that the variance is unknown. Okay? So based on this information, it is normally distributed and the variance is unknown. To find the confidence interval for the mean, we see that it falls in this scenario. So this is the formula we need to use. So this is the formula we need to use for the mean. And this is the formula we need to use for the variance. Okay? So now, let's start from for the mean. 98% confidence interval for the mean. And this is the formula. And in this formula, we need the sample mean, which is also given in the question, 127.442. We need the sample standard deviation, and it is also given in the formula. You take the square root of it, you can get S. The sample size n is also given because n is 0 to 30. So what we need will be just to find this T quantile. Since we are asked to find a confidence interval with 98% coverage, so 1 mass alpha is equal to 0.98. So alpha is equal to 0.02. So 1 mass alpha over 2 is equal to 0.99. So what we need to find is T 29 0.99. So you can look it up from the T distribution table. If you cannot do it, you can use R. If you still remember what you've done in some labs before, to find the quantile of a distribution, we can use the function that starts with the letter Q, followed by the name of the distribution. So Qt is actually a function that can be used to find the quantile from the T distribution. And you need to input the P, which is the 0.99. And the degree of freedom, here in this question, we need 29. So using this function, you can find the value of the T quantile we need for this question, which is 2.462. Okay. So we substitute everything into the formula. We have the sample mean 127.442 plus minus the T quantile multiplied to the standard deviation, which is the square root of the variance, divided by the square root of the sample size. Then the rest will be just calculations. Expressing this into a form of an interval, it is from 120 something to 134.24. Okay. So this is a typical way how we can find the confidence interval for the mean in case when the population is known to be normal and the variance is unknown. Okay. Now for the confidence interval of the variance, the 98% confidence interval for the population variance, sigma squared, we use this formula. Now notice that in the notes, you may wonder, in the notes, the form of the formula is not exactly the same as this. In the notes, you will find that the numerator here is expressed as sum of this square deviation. But actually, these two expressions are the same. The reason is that if you divide by n minus 1, you will get the sample variance. I use this just because in the question, the sample variance is given, so that we can just directly put into here. We don't need to try to find a way to find this sum of the square deviation. So what we need is the chi-square n minus 1, 1 minus alpha over 2, which is chi-square 29 and 0.99. And also this number, chi-square n minus 1 alpha over 2 equal to chi-square 29.01. To find these two numbers, again, you can make use of the chi-square distribution table, or you can use R. So we call that, to find the quantile, we start with Q. And then the keyword for the distribution, which is chi-square. And the input will be P equal to 0.99, degree of freedom 29, as before. And we also need to find the other numbers with P equal to 0.01. So from this, you can find it. You have 49.589 and 14.256. So we substitute into the formula the confidence interval for the population variance with the coverage 98% will be computed as the sample size minus 1, 30 minus 1, multiplied to the sample variance divided by the chi-square quantile. We just directly substitute everything we have into the formula for the confidence interval of the population variance. Okay. Now, usually for the estimation of the variance, the confidence interval obtained will be quite wide. You see, this is actually a wide range for the population variance. Is there any question? So the crucial procedure is to find the correct formula to be used. Once you can identify the formula, the rest will be just substitution of the numbers and routine calculations. Okay? Now let's just try to work on some other question that is not exactly finding the confidence interval, but it is related to confidence interval, which is the question number 5 here. So in question number 5, you're asked to determine the sample size needed to achieve a certain precision requirement in terms of the width of the confidence interval. Try to think about how to work on this question.
You know the question. It says find a 95% confidence interval for the mean reaction time has a width not exceeding 0.02. So what does that actually mean? The width is that like
width is the distance from the lower boundary to the upper boundary. Yeah.
That's what I'm thinking.
Okay, maybe I explain a little bit about the logic flow to solve this problem. Now, first of all, we identify some keywords, the normally distributed, so that we know that the samples are drawn from normal distribution. Also, we have the given sigma. Sigma is equal to 0.05. So the value of the population standard deviation sigma is given. So we can identify the formula for the confidence interval of the mean, which is given by this formula. This is the formula we can use in case when we have a sample drawn from the normal distribution, and also when sigma is known. But the question is not asked to finding this one. It says that we want the width of the confidence interval to be no greater than 0.02. So based on this interval, which is this interval, the width is just simply the distance from this point to this point. Or in other words, it is the value subtracting this number from this number. So it is just simply 2 times the margin of error, 2 times the quantile multiplied to sigma divided by square root n. And according to the question, we require this width to be no greater than 0.02. So we want this quantity to be no greater than 0.02. And we have already given the value of sigma. And this number, the quantile, can be determined according to the requirement on the coverage. And from this, we can solve the inequality to find the value of the sample size we need. So this is how we tackle the problem. We do it step by step. Find out the correct formula for the confidence interval. Based on the requirement, find out the expression for the width, and based on the requirement in the question, we set up an inequality according to that requirement. And then we solve this inequality. We'll find that n must be greater than or equal to Z1 mass alpha over 2 sigma divided by 0.01. Now it depends on the value of, we need to take the square. Okay. So it depends on the value of this. For example, for a 95% coverage, alpha is equal to 0.05. Z1 mass alpha over 2 is equal to Z.975 equal to 1.96. Again, you can find it from the standard normal distribution table or from R. So we put everything into the formula. 1.96 multiplied to sigma. Sigma is given as 0.05 divided by 0.01, and then we take the square of it. It will be equal to 96.04. So the sample size, the number of measurements we should take, should be greater than or equal to 96.04. And since the sample size must be an integer, so we will take at least 97 measurements. So it is actually a typical way how we can determine the required sample size to achieve a certain precision requirement. You see, when the confidence interval is narrower, the result will be more precise. Okay? So it is actually based on our requirement when we design a sampling plan. We need to know how large a sample we should take. Then we just try to, based on our requirement on the precision, we can determine the sample size like this. And you can try to work on the other part, because you're also asked to find the sample size we need in case when the 99% coverage confidence interval will have a width no greater than 0.02. Then you can just do the similar calculation by finding the correct quantile. Put into that expression, you can find the sample size we need. Okay? Any question? Now, so far, the formula we used are the confidence interval for the mean. Actually, there are some other questions in this worksheet. For example, in question number 3, I don't have enough time, so I will just work on this to show you the walkthrough of this question. So this is actually a problem about how we can construct a confidence interval for the population proportion. Because it says that we have a random sample of 500 households, and you have some sample data, 80 were found to have 3 or more TV sets. we want to find an approximate 90% confidence interval for the proportion of all households. Okay? So it is a problem of finding confidence interval for proportion. To find the confidence interval for proportion, from this summary, we see that we can use this formula. The approximate confidence interval for P is given by this. So we want to find a 90% confidence interval for the proportion P. And this is the formula we need to use. So we know which formula we should use. And in this formula, there are some quantity we need to determine. N is the sample size. It is given because N is 0 to 500 in the question. This is the quantile determined according to the requirement of the coverage of the confidence interval. So what we need will be the S bar, which is the sample proportion. And in this question, we are told that 80 out of these 500 households were found to have 3 or more TV sets. So the sample proportion of households with 2 or more TV sets can be determined as 80 divided by 500. So we have the last ingredient to complete the calculation. Now notice that the coverage required is 90%, so that alpha is equal to 0.1. 1 minus alpha of 2 will become 0.95. So this is, again, obtained from the standard normal distribution table, or by R. So we substitute everything into the formula. And you will find that the confidence interval for the proportion will be somewhere between 0.133 to 0.187. Okay. So again, this is a typical way how we can find the confidence interval for the proportion or a probability. Okay. Is there any question? So there are some more questions, but I don't have enough time to work through all of them. So you can refer to the solution that was uploaded to Blackboard, but you are recommended to just try to work on the question by yourself first. Okay? And if you encounter any problem, just feel free to send me an email. Now notice that the schedule of this semester is quite tight. After the end of the semester, probably you may need to have your examination or final assessment quite soon. Right? So you are recommended to do your revision earlier. So in case you encounter any problem, something you don't understand from the lecture notes, you can seek help from me. Okay? So see you next week.
Nice to meet you.
Nice to meet you. So you are from the other class?
Yes, I'm from his class.
I see.
Yeah, and there's a time to register, so.
That's fine.
Yeah.
That's totally fine.
Take care.
Bye bye.
Thank you.
See you.